Okay, we're going to handle angular motion with non-constant angular acceleration. So these are the cases where you have no choice but to use calculus to figure out your answer. So in the first section where we were talking about angular position, angular velocity, and angular acceleration, we came up with the following two relationships. One is that omega is equal to the derivative of position with respect to time, and that alpha, the angular acceleration, is equal to the derivative of omega with respect to time. And these are the equations you would have to use. If you were given a theta that results in an angular acceleration that depends on time, an example might be a sine of bt. If you take the derivative of this and then the second derivative of it, you see you get something where the acceleration is not constant. Because the acceleration is not constant, if you wanted to find omega, you'd have to take the derivative of this. You'd have to take the second derivative to find the alpha, the angular acceleration. So with cases like this, you're going to have to use calculus. Another example, this case, if you had an alpha that was something like e to the minus b times t, that's going to be another case where you have no choice but to use calculus. You want to find what future omegas look like, future angular velocities. You're going to have to integrate. You'll have to take this, do some substitution and some rearrangement. So here, if we did d theta dt, that would give us omega, and that would be, see, derivative of sine is cosine. We have to use chain rule. It draws a b out from the inside. So it would be a times b cosine bt. And d omega dt, the second derivative of theta with respect to time, will give us alpha, our angular acceleration. And now we've got a derivative of cosine, so we get a minus sine. So minus ab squared sine of bt. Vice versa, we went to start with an alpha and we went to get an omega. Well, we're going to have to take alpha dt equals d omega and integrate that. So we'll have integral of alpha dt is equal to integral from omega initial to omega final of d omega. And we're going to end up getting, let's see, well, for this specific case, we'd have to do a chain rule type thing, a u substitution. So a e to the minus bt dt would be equal to omega final minus omega initial. So we have to know initial conditions to make use of it. We'd integrate this from 0 to current time. Let's see. So we need a quick u substitution. That's going to mean dividing by a minus b. So it looks like we'll have omega final would be omega initial minus a over b e to the minus bt. Okay. I think that's the right idea. All right, and again, if you wanted to find theta, you would have to use omega is equal to d theta dt and rearrange. So you'd have omega dt equals d theta, and you integrate both sides. From your initial state to your final state. Okay, I'm not going to go ahead and do that one right at the moment. You get the idea at this point. You know how to do calculus. So that's the general principle. When you have something where the acceleration is not constant, you're going to have to sort of split it up. Deal with it in pieces. Okay? All right. That's all I have to say for this one, so I'm going to stop the video there. Next up, we're going to talk about what you do if you do have a constant angular acceleration.